Hey guys, and welcome to the review for our gases and pressure unit. So we're just going to rip through first all the stuff we've talked about in this unit, so you have some ideas about what kind of stuff you might want to study. And we're going to wrap up with a few examples just so you can kind of see how the math looks. So first thing we started with was the atmosphere and gases, right? So we started, oh, that's not my pen. Started with atmospheric composition, past and present. So what did Earth look like way back in the day? Mostly methane, ammonia, water, carbon dioxide. So that was where we started. After that, some plants came about, removed most of the nasty, harmful chemicals, which led us to today, where it is mostly nitrogen, roughly 78%, a good batch of oxygen, 2%, and then some argon, carbon dioxide, and other trace amounts. So all the rest of it together is like the remaining 2%. So mostly nitrogen, like vast majority nitrogen, fair amount of oxygen in there, and then some argon and carbon dioxide mixed in with a bunch of other trace gases. We moved from there onto pressure. So we decided to talk about pressure next and the definition of what pressure is. So pressure is the amount of force that a gas pushes on something with. It is actually measured in force per meter squared is the technical definition, or Newton per meter squared. Now that's a clunky unit to work with, so we work with all kinds of other units of force. Often we'll look at gas pressure in atmospheres. So 1 atmosphere is the amount of pressure that is regularly around us. We call what we experience every day a single atmosphere of pressure. So we are under 1 Earth's atmosphere of pressure right now. They come up with little machines to help measure these, and a lot of these little apparatuses used mercury. And so we measured the pressure of the air in how many millimeters of mercury were pushed up onto these glass tubes. So millimeters mercury is still a common unit, and 1 atmosphere is 760 millimeters mercury. We also often use a unit called pascals, named after the famous scientist Blaise Pascal, but pascals are really small. And so for everyday measurements, a lot of the time we use kilopascals, kPa. And 1 atmosphere is 101.3 kPa. So those are our common units of measurement that we use for pressure. You should be able to convert in between them. Then we talked about 3 of our gas laws: Boyle's law, Charles' law, and Gay-Lussac's law. So Boyle's law talks about if you increase pressure, if pressure increases, volume decreases. So as you pressurize something, it gets squished. P1V1 is P2V2. They are inversely proportional. Charles' law talks about if the temperature increases, we notice that volume increases. V1 over T1 is V2 over T2. So they are directly proportional. As one goes up, the other has to go up as well. And finally, we looked at Gay-Lussac's law. As temperature increases, pressure also increases. So again, a proportional relationship where P1 over T1 is P2 over T2. So you have all these different laws that can apply if something being held constant. So if, for example, the volume's not changing, then we're using Gay-Lussac's law. There's no volume here, it doesn't change. If you're holding temperature constant, then you're on Boyle's law. There's no temperature variable here. It's just if you're changing volume, what happens to pressure? If you're changing pressure, what happens to volume? And lastly, if you are holding pressure constant, then you could look at Charles' law. If all 3 are changing at the same time, you need something else. And that's our combined gas equation. And honestly, you can use this no matter what, as long as you remember that the one that stays constant just cancels itself out. So this is really the only equation you actually need. P1V1 over T1 is P2V2 over T2. So we got some experience with the other gas laws, but at the end of the day, the combined gas equation is probably our most useful one. So star that, very important. After we talked about the combined gas equations, we looked at standard temperature and pressure, also known as STP. Standard temperature and pressure has a temperature of 0 degrees Celsius, or 273 Kelvin, and a pressure of 1 atmosphere, or 101.3 kilopascals. That should be a lowercase k. Apparently my uppercase k and my lowercase k looks the same. Who would have known? Lastly, we looked into Dalton's law, which is talking about partial pressures. So the total pressure of a system is the sum of the partial pressures of its component gases. So if I had, pressure of gas 1 and the partial pressure of gas 2, the partial pressure of gas 3. So I've got 3 different gases with 3 different pressures all in the same container. My total pressure of the container is just these 3 added together. So if gas 1 was, 1 kPa, gas 2 was 2 kPa, gas 3 was 3 kPa, let's just say it was 1, 2, and 3, then I just add them. 3 plus 2 is 5 plus 1. It would be a 6 kPa total pressure inside that container. Another part of that we kind of looked at is that we figured out that a mole of a gas, no matter what gas it is, 1 mole of that ideal gas always takes up 22.4 liters at STP. So if you're at standard temperature and pressure, a mole is always 22.4 liters. What if you're not at standard temperature and pressure? How can you figure out how much it's going to take up or how many moles you're going to have? Well, that leads us to the ideal gas law. So if something changes, you need to figure it out. You do the ideal gas law. PV equals nRT, a super fundamental equation. Very important to know how to use this one. The only tricks to it, pressure must be in kPAs. Volume must be in liters. For all of these equations, it just makes sense to make sure our temperature is in Kelvin, if you're doing math with it, and then N just equals how many moles you'd end up with. Number of moles. Or if you know the number of moles, you can just plug that in there for N. And R is the ideal gas constant. It is always the same value of 8.314 for any ideal gas. Like I said, that number changes as you change temperature for non-ideal gases. But we're only going to look at ideal gases, so for all intents and purposes, this 8.314 is the number that you'll need to know. So R will always, 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 always be 8.314. Let's try one. I got a balloon, holds 100 liters of oxygen, or air. If I blow up this balloon with 3 moles of oxygen gas, so I got 100 liters capacity, I'm going to put 3 moles of gas in there. And it's under 1 atmosphere, regular atmospheric pressure. What is the temperature of the balloon going to be? So let's think about this for a second. We know at regular temperature, a mole's 22.4. Let's just call it 20 liters, right? So if I got 3 moles times 20 liters, I'd only be putting 60 liters into a 100 liter tank. So I know that 60 liters is going to have to get a lot bigger. How do I make gas expand? I increase the temperature. So before I even start, I know my temperature is probably going to be well above room temperature. It's going to have to be hot. So I'm probably looking at a hot air balloon. 100 liter balloon. That makes sense. So this would make sense for me to be, I should have a very high temperature when I'm done. Let's take a look, see what I got. Now I'm going to start with PV equals nRT because I can see that I've got volume. I can see that I've got moles. What else do I got? I got pressure, 1 atmosphere, which is 101.3 kPa, because I can't use atmospheres in my ideal gas law. What else do I know? Nothing. That's pressure. I need to find out the temperature. All right, let's plug in what we know. Pressure is 101.3 kPa. Volume was 100 liters. Number of moles was 3. R is 8.314, always. And temperature is what I'm trying to find. All right. So let's simplify the left side first. 101.3 times 100. There we go. And then we'll simplify the right side. 3 times 8.3. 3 times 8.314. How do I get temperature on its own? Well, I'd have to divide both sides by 24.942. So 101.30, no point because I times it by 100, divide by 24.942. Temperature equals 406.14. What are my units for temperature? What do I measure temperature in? Always and forever, when you're using math, In chemistry, we measure temperature in Kelvin. So 406 Kelvin, which means we are roughly 133 degrees Celsius. Yep, that is a very hot day to be filling a balloon, or you've got a fire underneath it because this is maybe a hot air balloon. So if that temperature is 133 degrees, what would normally be just over 60 liters of gas turns into 100 liters of gas because it expands with all that extra temperature. How many moles of gas? Okay, so I need to find number of moles. Are there in a 30-liter scuba canister if the temperature of the canister is 300 Kelvin and the pressure is 200 atmospheres? Whew, that's a lot of pressure. 200 times 101.3. Holy smokes. So just to show where that came from, 200 atmospheres, and I know that 1 atmosphere is 101.3 kPa. Changing out of atmospheres, I put it on the bottom. Changing into kPa, so I put it on the top. That's where that value came from. All right, let's plug it in. PV is nRT. So pressure, 202.60. Volume, 30.0 liters. Equals the number of moles, which I don't know. 8.314, because R is always 8.314. And the temperature was 300 Kelvin. Oh, that's an ugly 300. Let's try that again. All right. Same thing. I'll just solve my left side just because it's just a number. 20260 times 30. And then I'll solve my right side. 300 times 8.314. 2494.2 times the number of moles. So to get number of moles on its own, I take the 607,800 and I divide it by 2494.2. If I do that on one side, of course, you always do it on the other. So that cancels out. Divided by 2494.2. And it turns out our number of moles, there are 243.69 moles of gas in this 30-liter scuba tank. So if you think about it, I got a scuba tank. I want there to be a fair amount of gas in here, right? I need to breathe this for a long period of time. So by pressurizing the thing to 200 atmospheres, that gives you lots of room to pack gas in. 243 moles of gas. If you were to think of this not pressurized, 243 moles should take up, well, 22.4 liters each. If this was at STP, just out of curiosity, there would be 5,443 liters of gas in that tank. Whew, that should last you a good long time. That's a lot of moles. So you could stop here. This is all the question was asking for. But I was just curious, is how many liters is that? How much actual gas is cranked into that? In that 30-liter scuba canister, I've got 5,443 liters of gas if I was at standard temperature and pressure. It would be unpressurized and cooled down to the right size, the normal size, what we'd be used to. And that gives you a lot of air to breathe. All right, last one. It is not safe to put aerosol containers in a campfire because the pressure inside the canister gets very hot and then they explode. You're going to have a bad day. So I've got a 1-liter container. And it holds 2 moles of gas. The campfire temperature is 14,000 Celsius. That doesn't seem right. Oh, you know what? I bet that's supposed to be 1,400 and the degree sign turned into a 0. 1,400 is more like the temperature of actual fire. So let's just... Yeah, there we go. 1,400 degrees Celsius. What is the pressure inside the canister? So I did the thing I wasn't supposed to do. I threw my canister into the 1400 degree fire. What is the pressure? Well, first of all, liters, I'm good. Moles, I'm good. Celsius, not good. 1400 plus 273. So I'm at 1673 Kelvin. All right. Ideal gas law time. P equals nRT. Pressure. I don't know. Volume is 1. So far, so good. Number of moles. Ideal gas constant. And temperature. So, pressure times 1 is just pressure, which is what I'm trying to get. So I really just have to multiply this side and I'm good. 2 times 8.314. Oh, I put a negative in. 2 times 8.314 times 1,673. So there are 27,818.64, and units of pressure are always kPa. So let's divide that. I'm just out of curiosity. Divide by 101.3. That's 274.6 atmospheres. So our atmospheric pressure times 274. That is an insanely pressurized canister, which is why they explode. And that is why you do not want to throw them into a fire. So that kind of sums up our review. We went through a little bit of theory and stuff that we looked at. We looked at a few of the laws, and then we solved a couple ideal gas examples. So hopefully that is all the information you need to feel pretty confident in your abilities, and I will see you guys next time.